Today, I'm really excited to bring in a friend, Daniel, the CEO of Superlinked. So Daniel last time gave like one of the most popular talks on encoder stacking and reasoning about how to break down complex search queries. Like, if you want to search things like affordable hotels within a 5 mile radius of Manhattan, what does that actually look like? It turns out that one embedding isn't enough to do this kind of search, but maybe multiple encoders could help us understand to do this better. Earlier today, we had a call out on how do you rank things like time filters, right? And it's like, well, recent news, right, might want time filters that are recent, but if you search for the Wi-Fi password, maybe that document is 7 years old, but it's still relevant. And so there's a lot of nuance in how we think about things, and Superlinked is a company that helps us get that done. And so today I'm really excited for him to come in and talk a little bit more about, how we think about search and in particular, how we think about context engineering. For everyone who has any questions, feel free to ask them in the Slido. Marion will share a link below, and so you can ask your questions, upvote questions, and then we'll tackle the top ones as we wrap up this talk. And so, yeah, with that said, Daniel, take it away.
Thank you so much, Jason. Hey, everybody, again. Yeah, definitely today we'll be focusing on broadly relevance and performance of information retrieval systems. And I'll try to share some stories we collected by getting these systems into production with a bunch of companies, mainly around e-commerce and kind of internal knowledge management within enterprises. All my learnings are, let's say, for indexes up to 2 terabytes. So I don't know what happens past 2 terabytes, but that should kind of cover quite a lot of ground. Yeah, let's just get into it. Maybe just a couple words on my background. Before I started Superlinked, I was ML tech lead at YouTube, specifically in YouTube ads, and we were all about building systems for ad performance forecasting. When people buy campaigns, we gave them numbers of like, if you buy this campaign, it's going to give you this many clicks or views. Then they tweak the campaign, and once they like the forecast, they buy it. So I was an ML tech lead for that for like 6 years. And of course, we used a lot of representation learning and embeddings. So after that, I decided to see if this stuff can be productized somehow and made more accessible. Or will we forever be stuck in training custom encoders from scratch for any information retrieval or feature engineering task? So let's break this down a little bit. So kind of like number one thing, and you probably heard this from Jason, but I think this lesson bears repeating. When we talk to search teams in different companies, one of the things that jumps out is that they are not necessarily optimizing the right thing, right? So before you start to optimize your system, really identify, first of all, what is the framework? I like to use combination of these factors. So precision recall, obviously, those are in some kind of tension. You have cost, you have latency of queries, you have reliability, you have complexity of the system, and the compliance of that system to whatever rules exist in your company. And your, let's call it context engineering or information retrieval system, will be some kind of shape here, right? You'll do differently well on these dimensions. Being able to measure this and see where you are, I think it's a good first step. But this alone doesn't tell you where to focus your energies, right? This doesn't tell you, okay, well, we are doing somehow poorly on latency on the picture, let's go fix latency. This is what engineers tend to, they just kind of jump to, what is possible. And I would advocate for first asking, what does my manager want, or the PM thinks will help our users, or ultimately that's the kind of stuff that gets you promoted in these teams, right? So make friends of your product manager and get this out of their head somehow. And yeah, so there are really just kind of three steps to this. You want to find out what the person with the budget out of which your whole team is paid, or that's buying your solution. If you're a vendor trying to figure out these problems, you have to figure out what the problem is that they have already allocated budget to. So what's the business objective? Then you want to figure out kind of a lever that moves you towards that objective. And then you want some kind of iterative process of pulling on that lever. And, so I'll just kind of a little bit touch on this stuff, and then we'll get into the nitty gritty. But basically, your boss or your PM might say something like, okay, we want to sell more products, or improve support ticket resolution time, or we want to enable product teams to take data-driven decisions. These kind of sound like business objectives, but they really aren't, right? This is not super useful. What is useful is this kind of stuff. So basically, if you think about the objectives and key results framework, these are more like the high-level objectives. But basically, what you really want to get out of whoever owns the objective is what the key result is. How do we measure our progress? And so, sell more products by increasing AI search result click-through rate by 20% through improved relevance, right? It could be through UX improvements, right? Then it's not useful project. But for us, information retrieval people, okay, relevance is something we can do, and CTR is something we can measure. So this now starts to be interesting kind of input to a project, right? Or we want to improve support ticket resolution time by answering, helping the support rep answer their own questions against our system 10 times faster versus them doing their own research. Now, again, it's something we can measure. And similarly with the third example, and basically this is your input to the eval dataset, right? So the next logical step is that you figure out how to encode this in an eval in the first pass to start iterating your lever pooling activity against. And then, obviously you deploy it, you get feedback, you go from there. But basically, if you don't have this, it's a problem from the start. Anybody has sort of like issue here in trying to identify these things, or is this super easy? And usually in your projects, like exactly what's the metric, how it's linked to the business objective. I don't see the chat. Everyone's good. Okay. All right. So let's say you have established the metric. You have linked it to which of these properties, if you improve it, the metric moves, right? So let's say it's either the precision or recall when we talk about relevance, or the PM has an expectation that if we make the search faster, it's going to convert better, so with latency. So let's say you have converted whatever the previous statement was to kind of one of these things, and now one of these things is we know how to optimize, right? I do this vector search office hours, and just if you want to kind of benchmark against your peers, maybe you already shared this info within the group here, but this is some numbers that I got. So when I asked, I got 79 responses on this. What stands between you and the next production deployment of vector search? By far, the answer was relevance of the results, right? So people do POCs, but to do the full rollout, they still need to hit some kind of relevance target. And then this kind of cluster of like cost, latency, throughput, it's sort of related, right? You can throw more money at the compute and then improve latency or throughput. So it's kind of interlinked, but that's the rest of the field, basically. So I'm just going to assume that basically some combination of relevance and latency, let's say, is the kind of two things that are worth really digging into in your system. Okay. So now let's start with relevance, and this will sort of feel like somewhat assorted list of observations, and then we'll dive a little bit deeper into them. But basically, all of these are kind of established on real-world projects across kind of enterprise scale clients. So there was this. So just starting with the first point about evals. there was this kind of counter eval movement on Twitter lately, people saying, hey, don't do evals, just measure statistics in production, look at the user behaviors. I think it's still useful to have an eval. We always do, and I think it's useful. We split it into two parts. So we have kind of the same part of eval that the data scientists and ML people establish, and it feels that it covers a lot of the cases, a lot of the ground. It's sort of exhaustive in that way, and it feels robust to iterate the solution against. But then we also add this kind of observed crazy cases from production into a kind of separate bucket on there to keep in check how far the same part deviates from them and how well we are doing on those parts. So we find it useful to kind of call those out separately. And then what I see happen and going wrong a lot is once a team figures out the hammer, they want to apply it to everything, right? And this is, let's say, the team that we would work with, or they use a search vendor, and the search vendor gives them certain capability, and then they want to apply that capability everywhere, and we show them kind of a better way. And it has to do with also using our system. But I think re-ranking is an example that I would use here. Basically, once you figure out how to add, and it's very easy to do that, right? How to add some kind of cross encoder, re-ranker into your stack, then just giving it a few more candidates once you realize that the recall is not there, it's always such an easy thing, right? But maybe at some point, it's not worth adding the cost and the latency of doing that, right? So if you're already re-ranking thousands of candidates for each query, it's time to take a step back and see, okay, are we in some kind of local maximum over here? And do we have to start solving problems elsewhere? Like, for example, in the retrieval, at some point, it's the time to bring some of the signals down into retrieval and get the right stuff out of the database in the first place. So that's like a common trap that you can fall into. By the way, if there are any questions, I can also just come back to it if we have it on Slido, but I'll just kind of keep going. So the part I like about the whole like context engineering framing of retrieval is that I think people are starting to realize finally that not all the context is strength, right? Everybody is totally obsessed with like text tokens, right? This is what all the LLMs eat and produce, and what all the cross encoders re-rank, right? They understand all these entities we are trying to retrieve through the lens of stringification, right? And it's it's a really inefficient way to treat numbers, is to stringify them and then run them through a cross encoder. I think Cohere has this instruction following cross encoder that you can give JSON objects to, and you can say, hey, like prefer more recent results or stuff like that. But it's just, like trying to use a big hammer on something that in some ways is much simpler. Like if we have time in there and if we figure out how to blend these signals, we can do it directly without having to tokenize a timestamp and run it through a big model. And the same issue with the text embeddings under the hood. And that's typically where then things like boosting comes in, and then that kills the performance. And we'll get to that when we talk about latency. Okay, but basically TLDR, just really think about all the non-text and non-image data that's a part of your context assembly, and or part of the signals which you use to decide what should go into the context, and like start to treat those in a dedicated way. Another thing that I think is a big issue is at some point you want to have your agent prompt the retrieval system with natural language, or just the user directly wants to do natural language search. And in many cases, people go directly to like text to SQL, some version of text to OpenSearch query or text to SQL or some kind of variant of this. And if you really try to generate the whole, like any kind of query, it's slow and totally unreliable. And so I would suggest not doing that. Instead, I would suggest having a finite set of templates that are almost like tasks. Like, what are you trying to achieve with these queries? And each template basically somehow gives the outline of the query, and then you are using a language model to fill in those properties using, for example, the inspector library. And as you have those templates, you can start to optimize. Maybe use like you over time start to optimize the prompts for filling in the template components. Maybe look at the DSPY library for that. We had a lot of success in actually, let's say there is a query and we want to extract different kinds of intent from it. Let's say, does the user look for, is there some kind of recency intent? Is there some kind of popularity intent or location mention, things like this? We try to, use as small model as possible for this and run them in parallel for each parameter of the query. So there is some kind of query template and we want to populate individual fields in it. And we do separate LLM calls to do that, because then you can fine tune the prompt for each and it's much more focused rather than saying, hey, extract me these 5 things. To correctly do that, you need much bigger model, but extracting one intent at a time, you can first of all parallelize, and secondly, it can be much smaller model. And then, you can call these templates tools and make them discoverable for your agent. And now your agent basically can talk to the database, but not totally unconstrained generating any kind of query it wants, but only these kind of query templates, query patterns that you think are useful for it. Okay, happy to get back to that if there is a question. If you haven't really understood late interaction, now is like really the time, September 2025. It's super powerful technique. Just in short, I'm kind of assuming that everybody on here kind of tried it at least once. And we, for example, use it to optimize prompts, just for the chat. So late interaction has to do with kind of the suggestion number 6, which is stop pooling vectors more in general, but I'll get to it. Definitely worth looking into. DSPY for optimization, for creating kind of model independent LLM programs that you can then swap the model and re-optimize the prompt automatically. Very useful. Superlinked, we have a framework for creating dense vectors out of multiple encoders and stitching those together. I think I have slides for it, so we can get to that later. So like looking into frameworks, I think a lot of people used LangChain early on and then decided that frameworks all suck. I would suggest that you keep looking into stuff. And then let's talk about the vector pooling. So one of the first examples I saw out there in the world of trying to explain vectors to people was this. Who has seen this kind of thing before? Okay, see Ivan's hand. Basically, let's say it's a demonstration that you can do arithmetics on dense vectors. So in this case, we have a vector that represents the string king. We have a vector representing the string queen, and they're pointing to different part of the space. And we can do this thing where we subtract men from king, and we add woman to that result, and we get to queen, right? So this kind of arithmetic works, and this is how people get convinced that okay, there is this magical property of these vectors that you can average them and add them together, and the result will always make sense. What they don't tell you is that this is roughly the complexity at which this works, but if you keep doing this, immediately it falls apart. if you like, because here basically you kind of like average two things together, and that works. But if you start averaging a third one to it, it of course depends on what these three things are. But basically, that's already the point where this really stops working. And it's really helpful to build a good mental model for how this works. So one of the random examples that I show for this is that imagine you have these three strings. So red fancy shoes and cheap beach sandals and yellow high heels. So these are just three strings. We can make an embedding, right? And let's say that there'll be like, the position on the slide is where that string would be embedded on the scatter plot, and you can calculate their average, and that's over here. So let's say you have a system where the user interacts with products in your e-commerce store, and you are averaging together the representations of the descriptions of the products they clicked on, right? So they're building this user vector. Okay, so now let's examine how this looks. And one of the ways you can do it is you embed some more stuff and you see where it falls, right? So let's say footwear. So all three of these things are shoes, right? So we expect that if we embed footwear, it should be somewhere quite, in the neighborhood of the average of these three different kinds of shoes. And, okay, it's sort of in there somewhere. But if you try to do clothes, it's closer than footwear. So this is already weird. And by the way, the model I'm using here is the Qwen 3, I think the 600 million parameter model. So this is not some like bad model, right? This is the stuff that's on top of the MTB benchmark. And it would be the same with even the 8 billion parameter model. It doesn't really matter. So clothes is somehow closer to footwear, which already like doesn't make sense, right? Because you want to, let's say, recommend a product or do personalized search or something based on that averaging of the three products, and somehow you are now recommending clothes and not more shoes, but the user is clearly hunting after some kind of footwear. But this is the weirdest thing, right? So actually, the point nearest to the average of those three shoe-like things will be string that says skirts show flashing. Okay, so we have a string that like makes no sense that it's over there and it's there, and it embeds to the average of those three shoes. By the way, you can reverse engineer vectors in this way, right? Once you have an embedding, either you can kind of inspect the model and try to reverse engineer, okay, if this is the output vector, what would be the input to the model that produces that output? And you can kind of run an optimization over this. But even if you don't know the internals of the model, you can also still run this kind of optimization, right? You can start with some kind of string and swap tokens in and out and find the gradient and run an optimizer, sort of like DSPY optimizes prompts. You can run an optimizer that converges to a string that embeds really close to the vector that you have on the input of that optimization. So you can kind of reverse engineer what the vectors represent in a way. And this just shows you that the space is not as kind of smooth as you would expect, that, okay, I average these three shoes and I get some kind of shoe centroid. It's not really the case. So basically, long story short, stop averaging stuff. By the way, this averaging, or you can do mean pooling, so averaging or max pooling. You take maximum values of all these vectors that are combined. Those are interchangeable. That doesn't really matter. And you should be aware that you are doing this even without doing it explicitly. So let's say if I take like a whole document and I feed it into an embedding model and I get one vector out, this is basically pooled representation across embeddings of all the tokens in the document, right? So like if I have, if I feed one word into an embedding model, I get a vector for that one word. But if I have a single vector producing embedding model and feed it long input, in there somewhere internally it's going to aggregate embeddings of those individual tokens. And so basically I'm doing the averaging. So as a consequence, don't make single vector representations of documents, because this same behavior will be observed there, this kind of unpredictable convergence, let's say. So it's useful to make, vectors of tiny passages or like sentences, let's say, of a document. But then, of course, you have the context issue, like, how those sentences interact with each other. For that, I would look up late chunking, right? So you make the embeddings first and then chunk and aggregate, let's say, the token vectors for sentences. But you make those vectors with one big pass through the document before the chunking. Okay, so basically, you should really pay attention if you start to average vectors together. So that's the don't pool stuff. And by the way, that's like really related to the late interaction, because late interaction works because it doesn't average the vectors of the tokens, both for the query and for the documents, right? Late interaction keeps token vectors on the document side and token vectors on the query side and performs a bunch of queries with each token of the query independently, and then it adds up the results together. That's why it works, right? Because it doesn't pool. Okay, now fine-tuning. Okay, so we have sort of exhausted, okay, we are not pooling, we have pre-trained dense encoders for text. There is the empty EB table where we go choose those things, we look at the table on the task that's relevant for us, retrieval classification, we find a good model, probably is going to be Quen3 at this point, and we use it, we get the most out of it, we have an eval and so on. But at some point, you can extract additional value by fine-tuning. And I think this is more so for embeddings than for the actual generative models. I think with the generative model, you can do a lot with prompt optimization, but with embeddings, I think you can get the good edge from fine-tuning. But you should sort of know why you are doing it, right? So I'll give you a real-world example. In one of the projects, we were dealing with product reviews, and product reviews have this quality to them that it really matters how adjectives interact with nouns, right? So if somebody says this hotel has a good Wi-Fi, the good Wi-Fi coupling is really important, not just the mention of Wi-Fi. And the problem with any sort of pre-trained model, like Quen3, is that it's going to behave like this on this case. So this table shows correlate similarity between queries and hotel amenities. We have search queries on the y-axis. Let's look at the first row. So good Wi-Fi, and we are scoring the query good Wi-Fi against documents, which are these strings at the bottom. So good breakfast, good Wi-Fi, good pool, bad breakfast, bad Wi-Fi, bad pool. And you can see that, okay, like good Wi-Fi has a perfect score against good Wi-Fi. This is what we would expect. But then the second and third result are bad Wi-Fi and no Wi-Fi, right? So let's say you have built this amazing hotel search, and somebody wants hotel with good Wi-Fi. Now you will return results with any sort of Wi-Fi mentions in reviews. And if the mention is bad Wi-Fi, it's literally the opposite hotel of what the person is asking, right? So it's worse than no mention of Wi-Fi. So obviously this is like catastrophically bad result, and it's fixable with fine-tuning, because you can set up. So in fine-tuning, basically, you should think about it as, and I'm sure that this has been also covered in the course, but basically, the way I think about it is we are somehow trying to deform the space, right? We are deforming the space of these embeddings such that we optimize some kind of function. And in our case with the Wi-Fi over here, right now, because we see that here, right now, the good Wi-Fi, bad Wi-Fi, and no Wi-Fi exist somewhere together in the space, right? They're like a little cluster. And so they're all close to each other, basically. They're all close to good Wi-Fi. What we want to do is we want to pull them apart, right? We want the good Wi-Fi and the bad Wi-Fi string to be embedded far from each other. And for this, we can set it up as a triplet loss with a positive example of good Wi-Fi and the anchor of Wi-Fi and the negative example of bad Wi-Fi. And we can run an optimizer that basically pulls the negative thing away from the anchor and the positive example, right? So in this case, it's really easy to create these triplets. And with the sentence transformers library, this is like 15 lines of code where you set up the triplet loss, you feed it the triplets, you call the fit function, and it generates a model that then you can use that will properly, if I search for good Wi-Fi, the bad Wi-Fi doesn't register, right? So this is totally achievable. You need, small amount of data to do this. You should definitely do it. Another good case for fine-tuning of text encoders is if, let's say, you have a re-ranker, and you notice that, oh wow, the text embeddings, the candidates coming from that are, it keeps being worse, extending the set of candidates because the re-ranker finds some really good results further down the list, right? And the more this happens, the more it's a signal that there is some signal to be squeezed out, right? Because the re-ranker knows something that the embedding model doesn't know. And the more you see that the re-ranker pulls from like the 500th candidate, the more that's the case, right? And if you see that happening, then it makes sense to see if you can fine-tune the embedding model you use to look more like the results from the cross-encoder. Of course, it's not going to match it because cross-encoder runs the query and the document through this like much bigger network that has, complicated mechanisms inside that have more resolution, but we can kind of make the embedding model approximate this ranking that the cross-encoder produces by basically, having some kind of mean square error sort of reward or punishment for the optimizer. And yeah, we can, the reason this works is that you do it on documents from some kind of domain, right? So the embedding model is trained on whatever the data set is, but let's say you just have descriptions of e-commerce products, or you have some utterances from your internal knowledge base. On those, you can make the embedding model behave closer to the re-ranker. This is totally valid and should be done. And then you have to re-rank less and the whole thing gets cheaper, faster. And then, yeah, if you find it hard to mine for these kind of triplets and you just have negative examples, let's say the negative example is a random result from your data set, and the positive result is the one that, some kind of re-ranker or LLM as a judge identifies a really good result. You can, if you just have the negative examples, you can use a different kind of loss, and this also works in practice. So I think these are sort of the areas where we have had success, and you can get like 5+% precision improvements quite easily this way. But then you have the trouble of like, okay, how often should we retrain this thing? Now, if you use some kind of inference provider for embeddings that only has standard models, then okay, like they can't serve it, and you have to, the MLOps issues basically. But it can totally be worth it. Maybe last side note on this, there have been some papers that for the generative models, you can do a lot with prompt optimization. I would play with that for the embeddings as well. I would try to, you should think about prompt optimization similar to like low rank fine tuning, right? You are just changing like a thin thing on top of the model, in this case, prompt, that can, extract some value, and it's much easier to manage. So keep that in mind. And then how many of you have seen this paper? This was the, I think it made some rounds on Twitter as well, kind of last couple of weeks, by DeepMind on the kind of limits of dense representations, and also by contrast, they really sort of in that same experiment, the dense vectors came out poorly, and BM25 came out perfectly for that. I don't see the chat, and I don't see much nodding. Anybody saw this before?
I think I saw a little bit of it, but I haven't gone through all the details.
Okay. So I can give a quick summary because basically people read this thing and somehow decided in their head, okay, dense vectors suck. Like, let's not use dense vectors anymore. But it's that's misunderstanding of what this paper is doing. So let me just give you like a quick setup. So what these guys did was they constructed a data set, and then they tried to prove the like the number of dimensions required for a dense encoder to represent all the correct orderings of results for all the queries in the data set. And they have proved that the number of dimensions is insane. So through that, they're kind of trying to show theoretically there is an upper bound on the expressive power of single dense vector retrieval. And obviously, like that's true, but this is really the worst case scenario because the way they constructed the data set is literally like a sparse matrix. So it's a set of attributes like quokkas and apples in this bottom left corner. That's the rows, and the columns are people like John and Leslie and so on. And the whole data set is John likes apples or John doesn't like apples. And it's sparse, right? So a lot of this matrix is not filled, and it's totally random, right? So basically what this paper shows is that if you have a random sparse data set, then dense vectors will do poorly at trying to compress it, basically, or represent it. And this is like obviously true if it's sparse noise, then yeah, dense vectors are all about exploiting patterns in the data, right? That there is some cross correlation of features that can be encoded with the dense vector. If there isn't, then they don't work. But I'm assuming that the data you are trying to search through with dense vectors actually has relationships in it, right? So every time apple is mentioned, some other fruit might be mentioned, and so on. And in those situations, the dense vectors do perfectly fine. And of course, BM25 or sparse vectors do really good because they can just directly represent the sparse matrix that the data set is made out of, right? So this is not some slam dunk that BM25 is the best. That's right. So in the real world, like if you have a bunch of noise, don't put it into a surge index, right? That's kind of like in the real world. We have better things to do. With all that said, sparse representations are, I think, necessary. Like if you have any kind of, names of things or specific, acronyms, a lot of that stuff basically needs some kind of keyword search or sparse representation. And if you try to squeeze that out of the dense vectors, yeah, it's super inefficient, and you have to fine tune a lot, and you can just make your life easier by doing both, right? So the standard approach is that you combine a sparse representation of the data and a dense representation. And if your database allows single pass through the index where you score by both of the distances to those representations, then combine the score. This is the best thing. Second best is rank fusion, right? You do dense query, sparse query, combine the result sets by like interleaving them or something like that, and then re-ranking the whole thing at the end. But yeah, like definitely look into sparse vectors, and then Splade and other techniques like that are somewhere a little bit in between sparse and dense, but it's worth looking into. Okay, now we talked about text basically for all these different things. I mentioned the metadata a little bit, I think what is present in all of your data sets, most likely, will be some kind of relationship structure, right? Maybe it's explicit. This user clicked on this item. Maybe it's implicit, like the things mentioned in the document are also mentioned in other documents. But there will be some relationships, right? If you are doing this over some set of Postgres tables, there will be foreign keys in those tables. And graph rag obviously is a buzzword. I would, there is kind of the basic treatment of this topic, which is I'm going to use sparse and dense vectors and find some nodes in the graph and then look at the neighbors of those nodes to, let's say, expand the set of results and re-rank, right? This is the basic thing. Like you just look at the neighbors and you don't really need a graph database for that. It's kind of one join. The problem with this is that looking at neighbors of just the nodes you found is a local operation, right? It doesn't somehow exploit the overall structure of the graph. It sort of just looks at the signal available to that one node. Like, okay, you are linked to this and this other one. So you are leaving a lot of value on the table if you just, let's say, do this neighbor expansion. The way to take advantage of the overall structure of the graph, right? So let's say in the recommendations use case, the kinds of users like this user, like these kinds of products, and you aggregate all of this information across all the users and all the products, this is what a graph embedding is, right? It's just a way to compress the adjacency matrix and exploit the overall structure of the graph. And it's useful. We use it in all our e-commerce projects. And we try to obviously combine it with other kinds of features. So, Superlinked as a framework is all about combining encoders and making big vectors out of their outputs. And one of those encoders is a graph embedding encoder. And so the other benefit of graph embeddings is that the way you train these models is totally unsupervised. So you have your graph, you train an embedding. Now, if you feed it node IDs, it's going to give you some position in some space such that similar like nodes within the same neighborhood of that structure will project to a similar location. You don't need any labels for this because you are literally just learning how to compress the adjacency matrix. It's useful to combine this with other features of the data, because let's say if I have a new user doesn't have edges yet to products they interact with, then I need some other features to put them somewhere in the space. And some graph embedding algorithms do that out of the box. So they combine the node metadata with the link structure, like GraphSage does that. But the way we like to do it is we just focus the graph embedding on the structure of the graph, and we basically concatenate that with embeddings of the metadata, which are kind of purpose-built for the different metadata types. And this kind of combination of the content features with the graph structure is also basically this concept of semantic IDs. I think semantic IDs as a topic is something that you should just throw into Google. And I know Jason's friend Eugene is like obsessed with this topic. Just think about it as, let's say, training a language model on the tokens being some content properties of, let's say, products in e-commerce, right? So like a color or category, things like this. These are tokens. And then the language is the user interactions as they interact with different media, right? You have sequences of these interactions. User interacts with different tokens, different pieces of media with different properties. And then you can build basically a language model that can predict these interactions. Or you can just use the IDs as kind of descriptors of entities and then find similar IDs and so on.
Hey, Daniel, how many more slides do we have? I want to make sure we have a little bit more time for questions as well. Just want to double check.
Okay, Yeah, like 2, 3 slides, and then let's
Okay.
go into the questions. I can go also a little bit over time. So yeah, I'm sure some people have to run, but okay. So that was like a bunch of talking about relevance basically, and I wanted to touch on latency because that's kind of the other big topic with information retrieval. You know, if it's slow, it might as well not exist. Um, and we have been working with a lot of different vendors for vector search, because we work on this framework that's trying to, partner with a bunch of different databases. In the bottom right corner, we have this vdbs.superlinked.com, which is a table that compares 48 different databases on many different features. Throughout all this work, I have come to believe that there are really just two types of basically databases with vector search in them. And the types are, one is like full scan optimized databases. So these don't build some sophisticated HNSW index. They are just really good at full scan through the index, which means that you can do flexible scoring. You can, for example, combine the sparse and dense scoring in the one pass through the data. But to use these things, you need to pay a lot for compute, because each query has to sift through a lot of data, right? So if you don't have very selective filters, for example, you will pay a lot for compute. And then on the other hand, you have the kind of, let's say, more traditional vector databases that have everything in memory, and the memory dictates the price. And there is some kind of HNSW index in there that tries to prune the amount of data you are scanning through. And a lot of the time when the second category says that, okay, we launched metadata boosting, or we launched some kind of filtering functionality, it's before or after the approximate nearest neighbor index traversal, and that always causes recall problems. So that's something to be aware of, and I have an example of that. Just quick mention, you should benchmark the vector database, and typically they do pretty bad on concurrent reads and writes. And you should look at the fine print. So for example, we like to put temporal signal, like timestamps, into the embedding itself, and people go crazy on social media. Like, why would you put timestamps into the vector? It's crazy. But then if you go and, for example, this is OpenSearch example. Did you know, some of you use OpenSearch for vector search in this group. It's very commonly used index. And by the way, most of the other ones have the same issue. But in OpenSearch, if you do custom scoring, this is required to basically say, hey, I want to get recent results relevant for my vector search, combination of recency and relevance. If you do that, it kicks you into the full scan KNN algorithm, right? It's going to do a scan through the whole index, compare all the vectors, just so that it can do the scoring. Or it does approximate nearest neighbor search and then re-ranks on the time on the candidates that it found, right? So if your vector search query is broad, like, I don't know, pants in e-commerce context, this is not going to work, right? So like, really read the fine print of the underlying database and understand the trade-offs that the database might be doing for you. Your cluster might be 5 times the size it should be for these kinds of reasons. And yeah, this is the case in pretty much all the databases of the second type. Okay, and I mentioned this before, at Superlinked, we combine encoders to build vector representations that represent different aspects of the data in the same vector, so that you can just use the approximate nearest neighbor search index, and you don't have to deal with metadata boosting or re-ranking. There is simple math that goes into it, and that's it. That's the end of my presentation. It's an open source framework, Apache 2.0. You can use it for free. In fact, if you build something with Superlinked and tell us about it, and maybe write a few bullet points on how it went, we'll give you $500 and publish this under your name and kind of give you a shout out. So if you are into exploring stuff, just go to our GitHub. It's pip install Superlinked. There is the QR code as well. And with that, let's jump into questions. Oh my God, it took so long.
No worries, no worries. I think I'll try to be really selective. I think the one question I think folks are asking about is this idea of like text to query. How do you actually think about building these kind of things? Is it really just a prompt where you are just writing function calls? Are you fine-tuning different models to do this text-to-query generation? Can you
Mhm.
talk a little bit more about that?
Mhm. So one thing I mentioned is to break it into different queries. So you basically have, let's say you are trying to extract different types of intent, and I would do separate LLM calls per intent, and then optimize the prompt per intent, and then parallelize these calls. Because one of the problems with query understanding is the latency, right? We want to do it as fast as possible. And so having kind of smaller output, because you are just populating one parameter of the query template, does that, right? And you can also have much smaller models because you are extracting one thing at a time. And then, yeah, the DSPY optimizers are pretty good for this. And then, yeah, we had quite good success with like Gemini Flash, for example, the smallest hosted Gemini model. Also used, evaluated the smallest OpenAI models for this, but actually the Gemini Flash seems to be the best for query understanding right now. And then prompt
I see.
optimization.
So this is more like a sort of traditional search application rather than like having an agent sort of select out the tools, but kind of sort of like
Oh,
pre-computing what the tool calls would have looked like.
so I'm a fan of having tools that are quite like bigger task oriented, right? Like here are the 5 things, here are the 10 things you kind of have in mind when you go to this database, let's say, for the agent. And then I like to kind of describe like, okay, we have one pattern where we go in because we are looking for the most recent things the user did. And then I describe that properly, and I make a template for what do you have to fill in for this kind of query. And then I just show the agent like, here is one thing we can do with this database that's quite specific. So I don't just tell it like, here is a schema of the database, like go to town, because that's just, yeah, like is much harder to
I
constrain
see.
the latency on
So
that and harder to evaluate.
so it's almost like not only do you want to specialize on the tool, but you even want to specialize on the templates, right? It's like if you want to be computing like, month over month, year over year, like growth, you have templates for that rather than just saying like here's a schema. Yeah, I think that's sort of
Yeah,
a general consensus on building these systems. Like people talk about the better lesson, but we really want to specialize as much as possible.
yeah, yeah. If you saw, for example, the article Vercel wrote, like lessons from building like MCP servers and stuff, they also point to having these tools be much more kind of end-to-end tasks rather than the individual queries, because basically for the individual queries, you need to be able to inspect the output of the previous one really deeply and then design the next one. So if you are building a system against an API, you want super modular building blocks. If you have an agent that's trying to orchestrate this stuff, just give him sort of like he's gonna shoot once and get something done, and then can do something on the back end of it.
Makes sense. Let's do one more question. I know some people might have to jump off, but is it important to incorporate context from the surrounding document when generating these embeddings for individual chunks? I think a lot of this is our metadata. Like, how do you think about what other information outside of the string that you want to
Mhm.
include when embedding the
Who made the document, when, where in the company like structure they are, right? Team, group, all of this stuff. Some of it might be like access control. A lot of it is about relevance, right? If I'm looking for vacation policy, and I know that different parts of the organization have a different one, if I just look up against the content of these policies, they're all pretty much the same string with some couple parameters changed. And if you don't encode the like which part of the organization they, for example, come from, and don't reason about that the same way you reason about the content of the document, is not gonna work, right? So yeah. Um, Another way to answer that question is just the context list as much as you can find about the thing. So I like to start with just like everything, ideally, and then prune from there. Um, by kind of finding out if I remove certain things, how does the thing get worse, basically.
totally, totally. There's been a lot of cases where like we'll do document search of like internal data, and we find that we're never actually searching the contents of the document, but we start asking questions like, who modified this last, or who actually
Hmm.
responded to this email? And it's like, wow,
Hmm.
so many of these questions require us to have like an email address or a full name somewhere in the text chunk that we put in the tool response, so our agent can do something else afterwards, right? So it's also like,
Hmm. Hmm.
what is the question type and what is the side effect that we might have to trigger based on the data that we present to our users. And a lot of the time, it's like, oh, success is emailing them because they did something wrong, or figure out who changed this to ask why they changed it, or figure out who's using this table the most. Now I can know like what tips to get. Um,
Hmm. One thing to think about there is basically, you have, in my mind, kind of two sub problems. One is, how am I using all this information to surface the right output? And then how do I describe the output to the LLM? Because the LLM only sees through the text tokens, right? So the moment you put a timestamp in there, just know that it's gonna get tokenized the string and kind of misunderstood, right? It's not like if you ask this thing, hey, I gave you all these JSON objects and they have a timestamp property, can you, order them and reason about the timeline over here? That will always be noisy, right? It's not gonna do timestamp math correctly. It can trick you, it's doing it because it memorized like addition tables as string transformations, but there is a limit to this and it shows up in like super weird. Um, this is where some of the like weird errors come from. This is like way off in 5% of the cases. This is one of the sources of that.
Sweet. I think that's all the time that we have for today.
All right.
If all right.
Thanks a
Thank
lot
you,
for having
everyone.
me. Hopefully this was useful and see you around.
Thank you, Daniel. Take care.
Cheers.